Section 16.10, Acid-Base Behavior and Chemical Structure. When a substance is dissolved in water, it may behave as an acid, behave as a base, or exhibit no acid-base properties. How do chemical structure of a substance determine which of these behaviors are exhibited by the substance? For example, why do some substances that contain hydroxide groups behave as bases, releasing hydroxide ions into solution, whereas others behave as acids, ionizing to receive hydrogen ions? Why are some acids stronger than others? In this section, we'll briefly describe the effects of chemical structure on acid-base behavior. Factors that affect acid strength. A molecule containing hydrogen will transfer a proton only if the hydrogen X bond is polarized in the following way. In ionic hydrides, such as sodium hydride, the reverse is true. The hydrogen atom possesses a negative charge and behaves as a proton acceptor. Essentially, nonpolar hydrogen anion bonds, such as the hydrogen-carbon bond in carbon and methane, produce neither acidic nor basic aqueous solutions. A second factor that helps determine whether a molecule containing a hydrogen anion bond will donate a proton is the strength of the bond. Very strong bonds are less easily dissociated than weaker ones. This factor is important, for example, in the case of hydrogen halides. The hydrofluoric bond is the most polar hydrogen anion bond. You therefore might expect that hydrogen fluoride would be a very strong acid if the first factor were all that mattered. However, hydrofluoric acid has the highest bond strength among the hydrogen halides, as seen in Table 8.4. As a result, hydrofluoric acid is a weak acid, whereas all the other hydrogen halides are strong acids in water. A third factor that affects the ease with which hydrogen atom ionizes from HX is the stability of the conjugate base, X negative. In general, the greater the stability of the conjugate base, the stronger the acid. The strength of an acid is often a combination of three factors. 1. The polarity of the hydrogen anion bond. 2. The strength of the hydrogen anion bond. And 3. The stability of the conjugate base. Binary acids. In general, the hydrogen anion bond strength is the most important factor determining acid strength among the binary acids, those containing hydrogen and just one other element, in which X is the same group in the periodic table. The strength of the X anion bond tends to decrease as the element increases in size. As a result, the bond strength decreases and the acidity increases down a group. Thus, hydrochloric acid is a stronger acid than hydrofluoric, and dihydrogen sulfide is a stronger acid than water. Bond strength change less moving across a row in periodic table than they do down a group. As a result, bond polarity is the major determining factor in binary acids in the same row. Thus, acidity increases as the electronegativity of the element X increases, as it generally does moving from left to right in a row. For example, the acidity of the second row element varies in the following order. Methane is less than ammonia, very much less than water, is less than hydrofluoric acid. Because the carbon-hydrogen bond is essentially nonpolar, methane shows no tendency to form hydrogen ions and CH3 negative ions. Although the nitrogen-hydrogen bond is polar, ammonia has a non-bonding pair of electrons in the nitrogen atom that dominated its chemistry, so ammonia acts as a base rather than as an acid. The periodic trends in the acid strength of the binary compounds of hydrogen and the nonmetals in periods 2 and 3 are summarized in Figure 16.12. Oxyacids. Many common acids, such as sulfuric acid, contain one or more OH bonds. Acids in which the hydroxide groups or possibly additional oxygen atoms are bound to a central atom are called oxyacids. The hydroxyl group is also present in bases. What factors determine whether a hydroxide group will behave as a base or an acid? Let's consider the OH group bound to some atom Y, which might in turn have other groups attached to it. At one extreme, Y might be a metal, such as sodium, potassium, or magnesium, Because of their low electronegativities, the pair of electrons shared between the Y and O is completely transferred to oxygen, and the ionic compound containing hydroxide is formed. Such compounds there are therefore sources of hydroxide ions and behave as bases. When Y is a nonmetal, the bond is oxygen is covalent and the substance does not readily lose hydroxide. Instead, these compounds are either acidic or neutral. Generally, as the electronegativity of Y increases, so will the acidity of the substance. This happens for two reasons. First, the electron density is drawn towards Y. The OH bond becomes weaker and more polar, therefore favoring loss of hydrogen. Second, because the conjugate base is usually an anion, its stability generally increases as the electronegativity of Y increases. Many oxyacids contain additional oxygen atoms bonded to the central atom Y. The additional electronegative oxygen atoms pull electron density from the OH bond, further increasing its polarity. Increasing the number of oxygen atoms tends to stabilize the conjugate base by increasing its ability to spread out its negative charge. Thus, the strength of an acid will increase as additional electronegative atoms are bound to the central atom Y. We can summarize these ideas as two simple rules that relate the acid strength of oxyacids to the electronegativity of Y and to the number of groups attached to Y. For oxyacids that have the same number of hydroxyl groups and the same number of oxygen atoms, strength increases with increasing electronegativity of the central atom. For example, the strength of the hypothallus acids, which have the structure of HOY, increases as the electronegativity of Y increases. For oxyacids that have the same central atom Y, acid strength increases as the number of oxygen atoms attached to Y increases. For example, the strength of oxyacids of chlorine steadily increases from hypochlorous acid to perchloric acid. Because the oxidation number of the central atom increases as the number of attached oxygen atoms increases, this correlation can be stated in an equivalent way. In a series of oxyacids, the acidity increases as the oxidation number of the central atom increases.